All right. What if you look at the predictions? So here's the quality of the predictions. I made my machine. I chose, I forgot what the number is. I then take a noisy input from my library, and I put it into my machine. And I ask, what is the output that was generated from the noisy input, and how does it compare with the output I knew from looking in my library? That's my prediction error. And here's what you get from the calculation I described. If you make one measurement, you get a prediction error, never mind the absolute magnitude over here. We can scale that to what you want, which is up here. If I make 2 measurements, it drops significantly. If I make 5 measurements, it drops more. And at 10 measurements, the prediction error is saturated. So it says from the data set that I happen to have, 10 measurements is enough. My machine will tell you what's in that data set and give you good predictions. In fact, it saturates, you won't get better predictions. And that tells you how big a network to design. And it tells you how many data you need. And that question is simply not addressed in machine learning.
But how large is the number of cases with which you test your machine? And say that's
well, in our case,
that's how good my machine is.
Yeah, in our case, we took 100 samples out of the library. All right, but in fact, what this shows is that we only needed 10 samples out of the library. You could get the best prediction of the machine. What I'm arguing for here is that not that we have designed the machine. That was given in that nonlinear function that somebody chose. What we're doing is we're saying once you've designed the machine, your model, and once you have a data set that we can probe, we can tell you how much of that data set is needed by your machine to give good predictions. And we actually have a probe called action level plots that probes into that and reduces the reduces the methods that are used now, which are just you make it, you try it, and you see if it works. This will give you a hint about what it works. And finally, I'm not going to elaborate on this, but if a deep network has many, many, many layers, why not have a deepest network in which you make the layers continuous? And now I don't have to repeat for you. Once you've done that, you can now derive a differential equation that gives you the layers of the levels of your network as a function of your machine and this Tikhonov regularization parameter that we call RF. So you can take everything once you see the statistical physics analogy, and you can go into the literature and you can see how you can solve and address a lot of the problems that are just black boxes at this point. It does not tell you, to come back to your question, which machine should you design to start with. It tests that machine in a quantitative way. I believe that that is it. Thank you very much.